This discussion is about finding the derivatives of logarithmic functions. And we'll accept, for now at least, we'll see how to derive this a little later, but we'll accept for now that the derivative of the natural log of x is simply 1 over x. And of course we know that x has to be greater than 0 for this to make sense. And by the same token, we're going to, we could go through the chain rule version as we have in previous examples, in previous situations, but let's suffice it to say we'll accept that if we have the derivative of the natural log of an argument other than x, that is, u has something to do with x, but it's not x, it's still 1 over that argument, what we're taking the logarithm of, times the derivative of the argument. And once again, the expression u has to be something that would be greater than 0, otherwise it doesn't make sense to take the logarithm of it. So we'll accept those. So our first problem is about finding the derivative of the natural logarithm of x squared plus 1. And so we'll put up here how we find that derivative, but it ought to be straightforward for us. This is maybe one of the more simple derivatives that we've had to deal with so far. So the derivative of the natural log of an expression is simply 1 over the expression. So here it's 1 over x squared plus 1. And then we multiply that with the derivative of the expression. So in this case, that's the derivative of x squared plus 1. And as we've done many times before, we could have done this in our head, but we're setting up the situation so that we know how to do it when the derivatives are something we can't do in our head. So we have 1 over x squared plus 1 times the resulting derivative, which is 2x. And then we see that we can rewrite this expression, this fraction times 2x. Well, of course we can think of that as 2x over 1. I don't think that I'll do that in the future, but we'll certainly be able to write this then as the fraction 2x divided by x squared plus 1. And so we have our derivative and our result. Very straightforward. What I'd like to do here is to find the derivative of 4 different functions and a pair at a time, and I'm really wanting to have you look at the similarities but yet differences and how we actually calculate these derivatives. So let's take this first example. It's very straightforward, very much like what we did. We'll simply use the chain rule. So to find the derivative here, dy dx, well, it's 1 over the argument. See, it's 1 over what we're taking the logarithm of. And then we multiply with the derivative of the argument. Well, the derivative of 2x is simply 2. And then we see that leaves us with 2 divided by 2x, which is simply 1 over x. So there's our first example. Now over here, when we're asked to find the derivative, of course notice the difference in the placement of the 2. Here 2 is a factor on the outside, a factor of natural log of x, and here the 2 is a factor of the argument. And we recognize as good math students that these two are not the same. We cannot move a 2 inside and outside of a logarithm. So we approach this completely differently. And we do recognize in this case that we actually have a constant. So we actually have the constant 2 multiplied with the function natural log of x. So we'll simply use the constant multiple rule, that is, to find the derivative of a function that is a constant times another function. It's certainly just the constant times the derivative of the function. So this is just the 2 times the derivative of natural log of x. And of course, the derivative of natural log of x from what we saw before is just 1 over x. And so the result we get in this case is 2 divided by x. Clearly a different result, but of course they were different functions to begin with. Now I'd like to compare the next two functions, and we'll go about finding the derivatives here. So let's look at this first one. We have the natural log of x squared, and of course here again we're going to have to use the chain rule because we're going to find because our argument is not simply x. So the derivative of y with respect to x is 1 over the argument, so it's 1 over x squared, times the derivative of the argument. Well, the derivative of x squared is simply 2x. And so we see in our next step that we'll have 2x divided by x squared, and that will simplify to, oh, that's just 2 over x. Well, that's interesting. That's exactly what we got up here. In the next example, I'll explain why these are actually the same. But yeah, that's very interesting that we got the same result here. Okay. Well, in this example, we're faced with a different dilemma, and once again, compare where the exponent is. Here we're taking the natural log of something called x squared. Here we're squaring something called natural log of x. And so here the exponent being on the outside of the parentheses, we have to use the general power rule. And the way the general power rule would work then is to take the derivative to find dy dx. We would bring the power down as a factor in front. Then we would reduce the power by 1. So we have the natural log of x now to the power 1. But then we have to say times the derivative of what's inside the parentheses. And so in this case, the derivative of the natural log of x. Well, as we clean things up a little bit, we see that we have 2, and this is of course just the natural log of x in this position. And of course here when we find the derivative of the natural log of x, we just get 1 over x. And so as a result we have these factors times this fraction, so we'll end up with those factors in the numerator, won't we? We'll have 2 natural log x all divided by x. So again, comparing is the placement of these constants or the placement of these exponents make a significant difference on how we approach each problem. That's something very important to remember. Okay, well let's look at the next example. And actually what it boils down to is I want to compare or look at an alternative way to find the derivatives of these two logarithmic functions. We've already found the derivative in each case, but I want to look at a different method. And it requires us recalling the laws of logarithms. Remember, there are 3 laws of logarithms. The logarithm of a product is the sum of the logarithms. The logarithm of a difference is of a quotient is the difference of the logarithms, and the logarithm of an expression to a power is the power times the logarithm of the expression only. So let's get started with this first problem, and the idea here is before we actually find a derivative, let's use these laws of logarithms to simplify our situation here. So we'll rewrite y before we find the derivative of y. In this case, we have the logarithm of a product, so that says we can write y as the logarithm of the first factor 2 plus the logarithm of the second factor x. Now we're ready to find the derivative, and so when we're looking at the derivative of y with respect to x, then we have a sum. The derivative of the sum is the sum of the derivatives, so this would simply be the derivative of the first expression, natural log of 2, plus the derivative of the second expression, which is the derivative of natural log of x. Now here's a big point of recognition. The natural log of 2, although it's not something that we recognize quickly, this is just an irrational number. This is just some value of some long decimal number. It's only a constant. So what we really have here is the derivative of a constant. Of course, that's 0. And here we have the derivative of natural log of x, which is, oh, that's just 1 over x. And so in this example, we get the result 1 over x, which is exactly what we got earlier, if you look at your notes, but we just did it a different way. Now, that kind of gives us an idea of maybe how we're going to approach this next problem. And what I would like to remind you of before we go any further is we found the derivative of y equal 2 times natural log x, and the result we got was what? 2 over x? And that was the same result we got with this a little earlier. Same result we got here when we did it, when we did this derivative. And I promised to explain why. Well, here's why. If we manipulate, if we use a little algebra on this function before we find the derivative, that is, if we use the third law of logarithms, that is, we have the logarithm of x to a power, well, we can write that power 2 as a factor in front, so it's 2 times the natural log of x, which is exactly that other function that we had earlier, and we didn't notice that at the time. Now, now we find the derivative, dy dx, and of course we've done this previously. This is a constant times a function, so it's the constant times the derivative of the function, and of course the derivative of natural log of x is simply 1 over x, and so we get the result 2 over x as we had before, but of course we used a different approach. So sometimes it's very worthwhile to rewrite our function using laws of logarithms and then find the derivative. Well, as we're constantly reminded, anytime we learn a new technique, we can apply that new technique using old techniques simultaneously or in the same problem. You know, we may be asked to find the slope or the equation of a tangent line, or where the points on the graph where the tangent line is horizontal or some such thing. But anyway, let's look at this problem. We have a function y is equal to 2x to the fourth times natural log of x cubed minus 1. And in this example, we notice right away, I think, that we actually have two functions again. We have 2x to the fourth, and we have natural log of x cubed minus 1. So to find the derivative here, we're going to have to use the product rule. So we prepare to start. And let's see, to find dy dx, we'll require that we say first function times derivative of second. So we'll have 2x to the fourth, that's the first function, times the derivative of the second, and of course the second function is this logarithm, natural log of x cubed minus 1. And then we say plus the second function, which is natural log of x cubed minus 1, times the derivative of the first function. So it's times the derivative of 2x to the fourth. Okay, so we go back and find the derivatives that we can. Here we have 2x to the fourth. Let's see, the derivative of the log function is 1 over the argument, so it's 1 over x cubed minus 1, times the derivative of the argument, c times u prime. So the derivative of x cubed minus 1, of course, is 3x squared. Okay. Then plus, well, here we have the natural log of x cubed minus 1 times the derivative of 2x to the fourth, which we recognize as 8x cubed. And we see if we can't straighten things up and make this look a little neater. And we do that by noticing in this first term that we have the factor 2x to the fourth times this fraction times the factor 3x squared, which means these two factors will be in the numerator. And as we look at those and multiply them together, we'll actually get what? A 6x to the sixth. And of course that's the numerator, and the denominator is x cubed minus 1. And then we have plus this term, and normally we'll put this monomial factor in front, so we'll write this simply as 8x cubed times the natural log of x cubed minus 1. And of course here's our result. I don't know that there's much more that we can do with that, and so we'll stop it right here. Now, of course, this doesn't have anything to do directly with this problem, but I would like to mention, since that we talked a little earlier about using laws of logarithms and simplifying the function before we take a derivative, and I'd like to point out that there is no law. Remember, we have a law of logarithms that says if we have the logarithm of a product, m times n, that's the sum of the logarithms. That's the logarithm of the first expression, first factor, plus the logarithm of the second factor. That was one of our laws of logarithms. But if you look back at the laws, or if you remember the laws, there is no law that discusses what happens if you have the logarithm of things that are added together. The only addition you'll see is the logarithm is in this law, that at the end you have the sum of logarithms, but you never were taking the logarithm of things that were added together. And so there is no law that tells us how to deal with that. There's nothing that we can do further. That's as much as we can write it. So in this original expression, we could not have written that, by the way, as a logarithm of x cubed minus the logarithm of 1. Now here I use pluses, but it would be the same with the minus. So there's nothing that we can do from here, and I'm sure you remember that. Okay, let's look at this example, which is a little more involved. And notice what I've said here. Let's simplifying before differentiating. So we've seen a couple of simple examples there, but the idea here is before we actually try to find the derivative of this function, maybe we can use laws of logarithms to make it simpler and easier to deal with. And notice, as opposed to the last problem where we had a function outside the logarithm times the logarithm, here we just have the logarithm of things that are multiplied together. So it's a completely different setup than the last example, rather than function times logarithm. Well, what we want to do first is we want to take this expression, logarithm of x to the fourth times the square root of 3x squared plus 1, and first recognize that it's a logarithm of a product. So we can write the function f as the logarithm of the first factor, x to the fourth, plus the logarithm of the second factor, which is square root of 3x squared. And then I've combined a couple of steps, and one, we have the third law of logarithms that says, oh, we can bring this exponent 4 as a factor in front, so it's 4 times natural log of x only. We can think of square root as being a power of 1/2, and so I've brought that power 1/2 in front of logarithm, so it's logarithm of the argument 3x squared plus 1. But as we just discussed in the last example, we can't carry any, there are no laws that apply further to the logarithm of things added together, the logarithm of a sum. So this is as far as we can go. Now we're ready, though, to use our derivative information to find the derivative of the function f. So, and let's make sure now is when we're finding the derivative. So above was just simplifying. Okay, so we're going to say f prime of x. Well, f prime of x, to find the derivative of f, we recognize that we have a sum, and so we'll take the derivative of the first term, which happens to be, and maybe we should write that down. Let's make sure that we understand what we're doing. We're taking the derivative of a sum, and so we take the derivative of the first term, which is 4 times natural log x, and we add to that the derivative of the second term, which is 1/2 times the natural log of 3x squared plus 1. Now, as we look further, in this first derivative, we have nothing more than a constant times a function. So this is the constant 4 times the derivative of natural log of x. And we know the derivative of natural log of x is just 1 over x. So that's the resulting derivative we get there. Now, in this second term, we have a similar situation. We have a constant times the logarithm function. Well, to find the derivative, it will be the constant 1/2 times the derivative of the logarithm function. Well, to find a derivative here, we have to use the chain rule. But it's still 1 over the argument being 3x squared plus 1. But then we have to say times the derivative of the argument. The derivative of 3x squared plus 1 is 6x. Now, we're going to do some simplification here. So let's make a little more room. And we see that we have, of course, 4 over x in this first expression. And we have here, and now notice what's going to happen. We're going to have a 6 in the numerator, and we're going to have a 2 in the denominator. And so 6 over 2 is just 3, so we'll be left with a 3x in the numerator. And that's the 1/2 times the 6, or 3x. And our denominator will simply be 3x squared plus 1. Now be careful, don't do anything silly now and try to cancel these 3's or cancel these x's. Remember, we can only cancel if we have things in a factored form, and we have nothing factored in the denominator. Now there may be a little issue here, and I'm just going to point out, this is, for most instances, this would be an acceptable answer. And we might stop right here. But there are other cases, and there's sometimes in a book, or you're comparing your answer to the back of the book, that you see that you have one single fraction. And so that means we need to know how to actually add these two fractions together. So let's consider that. Let's suppose we were trying to go on. We need a common denominator, and of course that means it's going to be the product of these two, so we'll have to take the first fraction and multiply the first fraction by the numerator by 3x squared plus 1, and also the denominator by 3x squared plus 1. A little house cleaning here. So we're going to take the numerator and multiply it with 3x squared plus 1, and take the denominator and multiply it with 3x squared plus 1. And then over here we need to multiply both numerator and denominator by x. So we'll multiply with an x in the numerator, and we'll multiply with an x in the denominator, and of course we see that we have common denominators, and that's of course what we were expecting and planning on. Now, before we can actually add these fractions, we need to expand so that we can combine the two fractions, or the two numerators. So in fraction number 1, what we really have is a 12x squared plus a 4 in the numerator, just multiplying that 4 out, over our common denominator, x times 3x squared plus 1. In the second fraction, we simply have 3x squared, x times 3x. divided by that common denominator, x times 3x squared plus 1. Now we're prepared to actually add the fractions together by adding the numerators, and we see that, of course, we'll have a 12x squared and a 3x squared added together, so that's going to be 15x squared. And we'll have a plus 4, and of course the denominator is x times 3x squared plus 1. And then we would consider whether or not we could reduce, but since this numerator is not factorable, there are going to be no factors to cancel, and we may actually expand this denominator and write it as 3x cubed plus x. But this form or expanding would be fine. So this might actually end up being the answer that you would see in the back of the book, and so be prepared to be able to do a little bit more algebra before you finish the problem. Well, as we pose the question for exponential functions, how do we find derivatives of logarithmic functions that have a base other than e? For instance, how do we find the derivative of the log of x base 3? Or more generally, how do we find the derivative of log of some expression that's in x base a? Well, before we can answer this question, we need to remember some previous algebra. You know, this you may have learned in college algebra or pre-calculus. It's called the change of base formula. That if we have the logarithm of x base a, we can convert this expression to an expression using base b. That is, the log of x base a is the log of the argument, base b, divided by the log of the old base, base b. So now we have an expression that is in base b rather than base a. Now, if we're looking at the problem that we want to do up here, then we would be dealing with this form of that we have the log of x base 3, and we could turn that into an expression that was the natural log of x divided by the natural log of the base. That should have been a 3. This should be a 3 right here. So I apologize for that. Okay. Well, let me remind you how this happens. That suppose we're dealing with the log of x base a. This is what we're dealing with, and let's temporarily call that something n. Let's just call it by n. Now, using the definition of the logarithm, then we would know that this logarithm of x base a equal n means that if we take the base a and we raise it to the power n, then we get the value x, and that's what I've written here. Now, if we would take the logarithm of both sides, base b, the logarithm of this side would be equal to the logarithm of this side, base b, in both cases. Now, in the next line, I'm simply using laws of logarithms. I'm going to put this n power down in front of the logarithm, okay, as a factor. So now I've written this as n times the logarithm of a base b is equal to the logarithm of x base b. I'm going to solve for n by dividing on both sides of this equation by the log of a base b. So I'll be left with n on the left side alone, and on the right side I'll have the original right side divided by this factor log of a base b. So now I have n is equal to this fraction. But remember, n originally was just the log of x base a. So I can replace n with the log of x base a, and I have it's equal to the log of x base b divided by the log of a base b. So we've really just proven or verified this change of base formula. And we need to use that in this form. We need to use it in this form to be able to find this derivative. Well, I've made some space for us here so that we can find the derivative. Remember, what we're dealing with is y is equal to the log of x base 3, and we want to know the derivative. So the first thing I'm going to do, let's say the derivative of y with respect to x is simply the derivative, the derivative of the log of x base 3. But I'm conveniently going to change this logarithm form. I'm going to conveniently change this using the change of base. So I'm going to be doing nothing more than finding the derivative of, let's change it to base e. That's natural logarithm. It would be the natural logarithm of the old argument divided by the natural logarithm of the old base. And so it's simply this derivative that I need to find. Well, I don't want to really use the quotient rule. Let me write this for a reason I'll discuss in a moment. Let me write this as 1 over the natural log of 3 times the natural log of x. It's really the way I want to think about this. Now, when I go to find the derivative, let's recognize that natural log of 3 is a constant, so 1 over natural log of 3 is a constant. So this is nothing more than the derivative of a constant times natural log of x. Well, that's simply the constant, which is 1 over natural log of 3, times the derivative of natural log of x, which is 1 over x. Okay, which ends up being, let's rewrite this, and I'm going to change the order a little bit. It ends up being 1 over x times the natural log of 3. Now it's important here to kind of notice the form again. We could have just as easily dealt with a different base altogether. And so the point I'm trying to make is we'll compare with the result we got, but we could have been asking for the derivative of the logarithm of x base some general number, some constant number a. So in this case it was 3, but it could have been any base. And the result we will get, notice it's going to be 1 over the argument, but 1 over the argument times the natural log of whatever the base is. This natural log of 3 is just the natural log of whatever the base was. So it would be 1 over x times the natural log of the base, in this case a. And this is summarized on the next page. Now let's compare. The derivative of the natural log of x is simply 1 over x. But the derivative of the log of x base a is 1 over x times natural log of a. Now the chain rule version of the derivative here is the derivative of the natural log of u with respect to x is going to be 1 over that expression u then times the derivative of u. But if our base is not e, that is if we're working not with the natural logarithm, the chain rule version would be the derivative of the log of some expression, base a, with respect to x, will be 1 over the expression times the natural log of the base, and then that fraction is multiplied with the derivative of the expression. So we'll keep this in mind as we go about our next problem or two. Okay, in this next problem, we're to find the derivative of y equal log of 3x plus 1 base 10. And I recognize most of the time when we have base 10, that's called the common logarithm, we leave the base off completely and just write log. But in this case, I'm going to leave it there as base 10. So, when we're finding the derivative of log base other than e, then we have to remember that we throw in the logarithm of the base someplace, natural log of the logarithm of the base. So derivative of y with respect to x in this case. Okay, that's what we're looking for. Let's see how it goes. It's 1 over the argument. Well, the argument's 3x plus 1. But in that denominator, that needs to be multiplied with the natural logarithm of the base in our logarithm here. So it's the natural logarithm of 10. And then we multiply that with the derivative of the argument. The derivative of 3x plus 1 is simply 3. And so we quickly rewrite, and we'll have 3 divided by 3x plus 1 made more of a mess than I could imagine. 3x plus 1 times the natural log of 10. Okay, well let's look at our next problem. Here we're to find dy dx when y is equal to the log of x divided by 3 base 2. Now, I tell you, in this case, I think what I will do before I find the derivative, and there's actually a couple of ways. We could just leave this function alone and find the derivative based on the argument x divided by 3. But I find that that's probably going to be more difficult. Maybe we'll look at it both ways. But what I'm going to choose to do first is to rewrite my function. I'm going to use laws of logarithms. And I'm going to say, oh, the logarithm of a quotient is the difference of the logarithms. So this y is actually the logarithm of x base 2, the logarithm of x base 2, minus the logarithm of 3 base 2. Now I go about my business of finding the derivative. So dy dx is simply, let's see, the derivative of a log base 2 is 1 over the argument, okay, 1 over x, times the natural log of the base. In this case, that base is 2. But here we don't have to use the chain rule, do we? So we're not going to follow this up with the derivative of the argument. I suppose we could, because the derivative of x with respect to x is simply 1. Now, in this case, we have a constant again. The logarithm of 3 base 2 is just a constant, so when we take the derivative here, we get 0. And of course, we would just rewrite or simply not have put that in the beginning. Our result is 1 over x times the natural log of 2. And there's our result. Now, as promised, there's another approach here, one that where we don't use laws of logarithms first. So let's imagine what would happen if we used this other approach. That is, if we didn't recognize using the laws of logarithms. So we'll start out finding the derivative of an logarithmic function. Almost said an exponential function. And what do we have to do? Well, we have to say the derivative of log base other than e is still going to be 1 over the argument, and in this case that's 1 over x divided by 3 times the derivative of the argument, times the natural log, of the base of the logarithm, that's base 2. And then we have to multiply that with the derivative of the argument, the derivative of x over 3. Well, this looks significantly more difficult, and if we're not careful, we'll lose our way, and it will be significantly more difficult. But with a little algebra magic, a few things to recognize, let's rewrite this fraction before we do anything else. 1 over x divided by 3 times the natural log of 2, Now, to calculate this derivative, let's notice, this is an important observation that can be used many times. X over 3 is nothing more than 1/3 times x. So when we're finding the derivative of x over 3, we're really finding the derivative of 1/3 times x, and so we get simply the coefficient 1/3. If it was 2x, derivative of 2x would be 2, wouldn't it? So in this position, we actually get this derivative actually just being 1/3. Now that leads us, that actually helps us a lot rather than having to deal with this fraction in the denominator, which we might have to reciprocate. What we're going to have, notice in the denominator now, we have a numerator of 1, since we have 1 times 1, and we have this factor, and this factor. Well, let's rewrite it a little bit, and we're going to have the factor x over 3 times the factor 3 times the factor natural log of 2. And then clearly you see that our x over 3 times 3 is going to end up being simply x. So here we get x times the natural log of 2, which you'll observe is exactly the same result we got before, but I prefer the way we did it before, if you recall, was to first simplify the logarithm and then take the derivative, and it was much less trouble. Well, that concludes our discussion about derivatives of logarithmic functions and the chain rule in finding derivatives of logarithmic functions.